Good evening, class, and welcome to a lecture for Statistics 2023. Today, I'm going to be going through the Chapter 3 and Chapter 4 packet and basically just filling out the whole thing. You can also go and find the lecture videos with Professor Kilman filling out this packet. I'll use some slightly different words because I'm just going to be doing this freestyle, but I imagine that there will be quite a lot of similarity. So if you want just the two different perspectives, two different ways of describing the same thing, then please go check out those videos as well. In fact, I always encourage you to go and look at those videos and just get his perspective, as he has taught this course far more times than I have. So to start with, let's talk about the context of our statistics. We're going to be talking about performing experiments. And in this context of an experiment, we mean a process that produces exactly one observable, measurable outcome. So this might be a roll of the die, or this might be a temperature reading of the ocean water. This could be a count of the number of people that have a certain opinion. All of these things we can think as being an experiment in this context of statistics. It's a very general process. It's also sometimes called a trial. And we will see that a little bit more in the later Chapter 4 material that has to do with the binomial experiments. And what do we really mean by an outcome? Well, basically, this could be any phenomena resulting from the experiment. So an outcome of rolling a six-sided die might be that we roll a 5. That's one possible outcome. The set of all possible outcomes is called the sample space. You could think of it like the range of the possible outcomes. And an event is going to be divided into two categories, simple and compound, but both of them refer to a collection of outcomes satisfying some criteria. Criteria or properties. So when we have a simple event, this might be when a single outcome, so this is an event consisting of a single outcome. So example might be rolling a 5 on our die. And then a compound event is going to be complementarily an event. That's not how you spell that. Event consisting of more than one outcome. So for the die example, rolling a six-sided die, what about rolling an odd? an odd number. So there's many odd numbers on the six-sided die, 1, 3, and 5. And any of those would satisfy the criteria of the event. So we would call that a compound event. So what about probability? That's what we're here to talk about in this chapter. This is the probability topics. So probability is a numerical measure of the likelihood, which just means how likely is something to happen, of an event or outcome. It's a simple event. And there's two rules for assigning a number to an event to indicate its probability. I will call probability usually P of E, like this, and that's the probability of event E. And it's got to be a number between 0 and 1. You cannot have a probability less than 0. You cannot have a probability greater than 1. We think of 0 as meaning infinitely unlikely. And in the case of sort of finite classical probability, that might be impossible. Or having a probability of 1, which might mean almost surely to happen. Or in the case of what we're going to be talking about, discrete finite probabilities, that might mean certain to happen. And the other property is that the sum of all the events in the sample space, so let's say that the sum of all probabilities E, where we're summing now over every single event in the sample space. And perhaps it would be better if we considered these to be all simple events, or we could say the sum of all outcomes, the probability of each outcome in the sample space, I think might be a better way to do this. This has to be equal to 1. So the sum of the probabilities of all events, or better yet, as I said, all outcomes, is equal to 1. And the way that we could interpret what that means is that given that an experiment has happened, some event or some outcome is obtained. One of the things that we will say about an experiment is that it produces exactly one observable outcome. In other words, it doesn't produce no outcomes, or we wouldn't say that was an experiment that was valid or well performed. So basically, this is saying that the probability that we get at least some outcome is certain. And we insist that the sum of all probabilities of every outcome totals to 1. We'll look at some examples later that'll kind of flesh that out, but suffice it to say, these are your two main rules about probabilities. If you add up all the probabilities, it's 1. Every one of those probabilities is between 0 and 1, inclusively. So in classical probability, all outcomes are equally probable. Think of the six-sided die again, right? The classical probability says that the probability of getting a 1 is the same as the probability of getting a 2 is the same as the probability of getting a 6. They're all the same probability for every individual distinct outcome. And I just want to comment that means that we can interpret the probability of an event as being equal to a ratio of the number of ways the event is possible, or the event happens, divided by the number of ways, the number of possible outcomes. If all of them are equally probable, then this kind of naive interpretation of what is the probability of an event is perfectly valid, right? You just count the number of ways that an event could happen. Basically, these are the number of outcomes pertaining to some event. And then you divide that by the total number of possible outcomes. And this you could think of for finite probabilities is the size of the sample space. We're not going to be able to use that when we talk about continuous probabilities or infinite numbers of possible outcomes. But for right now, what we're just talking about, oh, I've got this die. It's got 6 sides. I roll it. What's the probability that I get an odd? Well, the probability that you would get an odd is going to be the sum of the number of ways you get an odd, say 1, 3, and 5, that's 3 different ways, divided by the total number of possible outcomes. There's 6. So 3 divided by 6, that's 50% or 0.5. Now, what about this second one, relative frequency probability, also called empirical probability. Empirical probability or relative frequency probability, this refers to when we've already done an experiment. So we perform an experiment, say n times, and observe event A f times. Then we would say that the empirical probability is equal to f divided by n. Right? Again, it's sort of a ratio compared to the total number of something. But here we're talking about the number of experiments we did. So let's say we did 100 experiments. And let's say in 18 of them, I had a certain property. Then 18 divided by 100 would be the relative frequency probability of that certain event having that property. And we'll talk more about this, but this is sort of descriptive in a sort of it's a descriptive number, right? You get the experiment, you do the experiments, and then you could measure how many times something happened and divide by the total number of experiments you did. This is sort of reflexive. On the other hand, probabilities, assuming that they're equally probable, calculating the number of ways they could happen, dividing by the possible outcomes, you could do all of this before you did the experiment. So it's proscriptive, it's predictive, right? So classical probability is a kind of theoretical probability where you are prescribing a likelihood to an event. And relative frequency probability is reflexive or descriptive, where you are describing how many times an event was actually observed in a real sequence of n experiments. Subjective probability, I won't say much about. This is, intuition, subjective judgment. This is non-rigorous, right? This is when you say, well, that's likely to happen, or I give that about 50% probability. Did you in colloquial speech, you might not have made any calculation to do that, right? It might just be based on a hunch or a gut feeling, and as such, we just want to distinguish that so that we can say, okay, well, we're not going to do that, right? In this class, we want to talk about mathematical approaches to probability and not, sort of less rigorous ways of assessing a likelihood. Now, is subjective probability sometimes based on your own personal history a kind of relative frequency probability? Yes, in the best case scenario, it is. But it's also, when we say subjective, we're implicitly meaning that there's a kind of, perhaps a bias, a personal bias that's going on. We mean to distinguish it from more rigorous methods. You wouldn't calculate a subjective probability. We would calculate a relative frequency probability. All right, let's look at some examples to kind of flesh this out, right? What is the probability? So it says a fair six-sided die is tossed, is rolled once. Let's talk about fair, right? Fair means all sides equally likely. So that means this is classical probability. We might talk about unfair dice later. Six-sided, right? This is the size of the sample space, right? The sample space then, I'll just write S for sample space, right? S is going to be the rolls. 1, 2, 3, 4, 5, and 6 are possible then. And we roll it once. So we're going to select one of these outcomes at random. What is the probability that a 5 occurs? What is the probability that a number less than 5 occurs? And what type of probability are these examples? Well, they're both going to be classical because we are considering them to be equally likely on each side. Right? There's a number of outcomes, 6, and all we have to do for a classical probability is to count the number of ways that each event is possible. How many ways are there to roll a 5? What is the probability of a 5? Here I'll say X as being the value of the dice roll. What is the probability that it is 5? Well, how many ways are there to roll a 5? Only one. There's only one way to roll a 5. You roll the die and the 5 side comes up. So this is a simple, right? This is simple event. And then how many ways were there to roll anything? There are 6 ways. And if we looked at this as a decimal, of course, this is 1.6 repeating, or, well, I shouldn't say approximately, it's exactly 1.6 repeating, or 0.16 repeating. That's approximately 0.1667. We wanted to round it to 4 places. On the other hand, what is the probability of X being less than 5, strictly less than 5? Well, how many different ways can it be less than 5? Well, there are 1, 2, 3, 4 values less than 5. And so this would be 4 ways that could happen, divided by 6 ways that anything could happen. And what we wind up with then is 2/3, or 0.6 repeating, which is approximately 0.6667. This is a compound event because there are more than one outcome pertaining to being less than 5. 1 is less than 5, 2, 3, 4, all less than 5. And so more than one outcome is necessary to give us, it has to be taken into account to give us the correct probability. Okay, so it says, suppose a fair coin is tossed and tails observed 27 times. What is the observed probability? Right? Observed probability, aka the relative frequency probability, aka the empirical probability. All those are synonyms. They all mean the same thing. What is the probability of obtaining a tails in terms of the estimation given by the relative frequency probability? We know if it's a fair coin, we know what the probability is. 0.5. There's 2 outcomes, heads or tails. What's the probability of getting each one? 1 out of 2. Okay? So that's the classical, that's the theoretical probability. This says, no, we did that. We rolled it 50 times. The frequency was 27. The number of times we rolled was 50. And so my relative frequency probability is F divided by N, aka 27 divided by 50. And as a decimal, right? That would be 0.54, right? A little bit bigger than 50%, but that can happen with relative frequency probability, right? We're not saying that it's actually equal to that, right? What type of probability? Relative frequency probability. We're not saying that in any given outcome, you're likely to see exactly the theoretical probability. We only expect that to be sort of something that's close by. And what we can do is sort of define mathematically what we mean for it to be quote unquote close by. That's this law of large numbers here. What the law of large numbers says is that for n large, f over n. Oh well, let's define our terms here. Where f is the frequency of event A in n trials, we expect f over n to be approximately equal to the probability of A. We could say this a bit more strongly. We could say that f over n goes to or approaches the probability of A as we allow n to get arbitrarily large. If you pick some humongous number for n, we expect it to be very close to the probability of A in terms of its relative frequency. It says that if you do enough trials, you should get something close to the probability of the event in terms of the relative frequency probability. However, even better would be to say the last bit here, which says as n goes to infinity, the difference between f over n and p of a becomes arbitrarily small. You can make that difference as small as you like by taking n sufficiently large. Now, what it doesn't tell you is how large an n you need, and it won't, and it can't. This is random behavior, right? It's truly random. When we think about rolling a die, maybe from some perspective that's deterministic, but for the person rolling the die, they have no chance of calculating that probability. The likelihood of any single face rolling is going to be equal, and we interpret this as meaning that there's no way of predicting the outcome beyond the probability, right? So we don't know when it's going to be equal or how close it's going to be or how big n needs to be in order to get it close. But the law of large numbers says as n gets larger and larger, this thing will drift towards the probability. F over n will drift towards the probability of the event A. That's all I'll say about that. Now, the last one is a subjective probability. I'll gloss that over. It says a student believes he's got a 90% chance of passing since he's pretty good at math. Okay, so he's using a colloquialism. What does 90% mean here? It's a feeling. Nearly sure. Right? Not maybe he's giving himself some wiggle room. Maybe there's a chance that he'll fail, but he feels pretty sure about it. Right? That's again. This is a subjective probability. Right? There's no metric that he's using. He's just implying that something about this seems that it's more likely than not. Right, and that's probably as far as this needs to be taken. Right, subjective probability by use of the word like belief. Right. If it's a relative frequency probability, it has to do with historical data. It doesn't have to do with belief. Right. If it has to do with belief, right, this is a subjective judgment. Okay, so in order to talk about the way that logical conditions like or, and complements and such, in order to talk about how those combinations of events will relate to the probabilities of those events, we first need to talk a little bit about set theory, right? Because we're going to be working with events as being subsets of a sample space, and we're going to be working with the sample space itself as a set, right? So we've got as the universal set for our situation, right? The sample set you could think of as being the set from which all possible outcomes are drawn. So this is sort of like the universal set if you've had any exposure to set theory. If not, don't worry about it. I'll try to give you everything you need to know to kind of suss this out. But before we talk about sample spaces and universal sets, we can talk about and or and complement conditions. Well, we actually, that's not true. We need the space. We need to talk about that in order to talk about the complement. But to talk about ands and ors, we don't. We can just look straight at these things. So an or event is an event satisfied by either the criteria from one or another set. Let's call those events. So let's say these are our possible outcomes, 1, 2, 3, 4, 5, that pertain to an event A. And for B, we likewise have 4, 5, 6, 7, 8 that pertain to an event called B. And now we want to say, well, what's A or B? What would that event be? Well, I want to talk about, in this case, right, the union A or B as an event is going to be the same as the union of A and B as sets. Right, we're saying either you're in the first set, in which case maybe you're a 1, a 2, a 3, a 4, or a 5, or you're in the second set, in which case maybe you're a 4, a 5, we don't need to list those again, but perhaps a 6, a 7, or an 8. So we take the set complement, and now these are the list of possible outcomes which would satisfy the condition A or B. So an and event is going to be sort of not the opposite of that, but it's sort of asking a separate question from that, right? Instead of having it satisfied by either being in the set A or being the set B, we need an event. An and event is satisfied only if both criteria for of two sets of two events are satisfied. So I like to think of this as you have to be in both sets, and we have an arrangement for that. I could say that A and B as events would be the same as looking as the set of outcomes A intersect B as sets. So we ask, what do they have in common? Right? This is the set of them together. This is asking, what do they have in common? And what do they have in common? Well, they've got a 4 and a 5 in common. So that's their intersection. And if I wanted to say, what is the event A and B, right? If we have these two different events, right? Event A, which is made up of outcomes 1, 2, 3, 4, and 5. Event B, which is made of outcomes 4, 5, 6, 7, and 8. And I say, what is the event A and B? Well, there's only two things which satisfy both A and B. That's 4 as an outcome and 5 as an outcome. So that becomes our new event subset. So complement, which is also sometimes called logical knot, right? You need to talk first about some kind of parent space, some kind of sample space of which the thing that we're going to take the complement of is a subset. So given a an event A, a subset of S, which means that every element of A is an element of S. The complement is everything in in S that isn't in A. So it's sort of like not A, where not is understood to mean all the things that are not in A but are still in my parent set, are still in the universal set, which includes A. We will call that the sample space for statistics classes. So, for example, if this is our parent space, right, and our set A is 1, 2, 3, 4, 5, then the complement of A, which is sometimes either written A complement, but there's many symbols for the complement. You know, A tilde. I believe your book uses A prime, or many books use A prime. Not A is another one. All of these mean the complement. I might go back and forth between a couple of these that are my faves. I like C because it says like complement, and you can just like see it right there. You could even say not A. That's also fine. So all of these are sort of synonyms for, or not even synonyms. They're alternative symbols for not A. They all mean the same thing. So what is this going to be? This is going to be the set of things which are in S but aren't in A. So if it's in A, we don't use it. So none of this works. The only thing that we do take from S is 5 and 6. And so the complement of A in S would be the set 5 and 6. Notice a couple things. Notice that in that definition, A and A complement together make the entirety of S. Note also that their intersection is empty. You cannot be both in A and not in A simultaneously, right? So in some sense, they span a set and its complement, span or make up all the possibilities that could be. And their intersection has to be non-empty. We sometimes call that the law of the excluded middle, or just basically think about it, you can't be a thing and not that thing at the same time. Not for well-defined statements and predicates and that kind of thing. Right? I mean, notice that A and not A here have nothing in common, and that's the idea. Okay, let's go on to the next one. So conditional probability is different in that it doesn't really have a logical operator that goes with it, but it's sort of easy to understand. We say that the probability of A given is the special word here. Given B means knowing B has happened already. What is the probability of A? So this sort of starts to get into a certain aspect of time in this, right? We have to say that, look, we know that B has happened already. That's gone on. What is now the probability of A. Maybe it's the same as the probability of A. Maybe knowing that some other event has happened changes the probability of A itself, right? Maybe, so for example, let me zoom out for just a moment. Okay. Let me get a little example space. Where can I put an example? Let me put it above here. Right. Let's say the probability that I wear my boots. So the probability of Sean wearing boots is, I don't know, 0.15. But if it rains, if I know that it's raining, the probability of me wearing my boots is 50% or 0.50. So we might say, this is the probability of me wearing my boots. But we would also then say, in this case, this is the probability that I wear my boots, given that, so this little notation means given. This is what conditional probabilities look like. Given that it is raining. And we'll talk more about how these probabilities change, but suffice it to say, we want to talk here about Bayes' theorem. So I'm going to do a little bit of work to the side as well. Maybe if I go over here, I can put this work. It has to do with calculating probabilities for and or conditions. So let me go back here. And let me, I don't know where it's going to pop up in the in the worksheet. So let me put the formula down for these, right? The probability that A and B happen. What is that? We want this in terms of the probability of A and the probability of B. Like we want how do I write this in some kind of formula that involves the probability of A and the probability of B, right? And so well, it's getting a little busy down here on this page. Let me go back up and I'll put this up top here, right? So we would say that the probability of A and B, and I'll also include this in the sheet when it pops up. This could be calculated one of two ways. This is either the probability of A, and then we could times that by the probability of B. And why does this make sense, right? We're saying first of all, what's the probability that A happens? There's a certain percentage of the time that happens. And then a percentage of that time, B happens. So we want to take the percentage, the proportion of these times that A happens, and then take of those the percentage of the time that B happens. But wait, we already know that A has happened in that case. So there's a relationship between and, the linking of two probabilities, and the product of the two probabilities. I'll try to justify this equation a little bit more, but if you take this for granted, you probably could guess a little bit about where this is going. There's no sense in saying the probability of A and B or the probability of B and A, right? And just means both of them. And so it doesn't matter which one I say first. And so what we could also say then is that this is the probability that B happens, and of that percentage of the time that this happens, what percentage of the time does A happen? But wait, of the percentage of the time that B happens, we already know B happened then. So this is actually not just the probability of A, but the probability of A given B. So here, but now I have this chain of equalities, and what does it really tell me? Right? It tells me that these two are equal. And that's pretty cool, because those don't necessarily look equal, right? This says that the probability of A times the probability of B given A is equal to the probability of B times the probability of A given B. And this is what is usually called Bayes' theorem. I believe in your book it is given as just this first statement. But I would prefer to think about it in terms of omitting the and probability and saying, look, actually, this is a relationship between these two probabilities and the conditional probabilities. There's numerous ways that you could express it. You could divide P of B over, you could divide PBA over and write it as a ratio of the givens versus the reciprocal ratio of the probabilities. There's a lot of different ways to express this fact. But I think for the purpose of our notes, let's just say that this is going to be a relationship indicating how and probabilities play out in terms of givens. You want the probability is meaning, roughly speaking, the proportion of the number of times that something should happen, that we should observe event A. And then timesing by that, the proportion of the number of times that we should observe event V, given that A has already happened, right? We are now considering not just that B is happening, but that it has happened after we know that A has happened, right? Once we say P of A, we've assumed that we are in the proportion of worlds where A has happened. That changes the probability of B happening possibly, right? So let's look at an example with some dice to try to shore up our understanding of these new terms like given. Okay, so fair, six-sided die, describe the sample space, identify the events, compute their probability. Okay, so what is my sample space? It's a six-sided die. So 1, 2, 3, 4, 5, 6. These are my possible rolls of the die. What is the probability that we get a 2? Well, how many ways are there to roll a 2? Keep in mind, we're not plugging in 2 here. We're not plugging the value. We want the number of ways to get a 2. There's 1. And there's 6 total ways of doing anything. So there's our probability. Again, something approximately equal to 16.67%. What about the probability of A? It's an even number. Well, the probability that's an even number, how many ways are there to be even? 1, 2, 3. There are 3 ways to be even divided by 6 ways total. This is a 0.5 probability. Same thing with the probability of B. Oh, I'm sorry. This is the outcome is less than 4. Well, less than 4 means strictly less than 4. So that's 1, 2, and 3. So there is still 3 ways that's possible out of 6 total ways, 0.5. And then it says, what is the complement of A? Well, the complement of A, is that it's an odd number. It's all the other things, right? A key thing to keep in mind about probabilities, remember we said that the sum of over all the outcomes has to be equal to 1. Well, an event and its complement include all the possible outcomes. That's it. So just to go back here to complement for a moment, I want to put one more note down here, right? If I have the probability of some event A and the probability of its complement, that's the sum of all possible options probabilities. That has to be 1. And what this tells you is that if you know the probability of A, you can calculate the probability of A complement. Just take it away from 1. And that's how I usually like to proceed when they ask me, hey, what's the probability of the complement of A? Well, it's 1 minus the probability of A. So it's 1 minus 3/6. Well, but that's also 0.5. Right? Complement of A is actually the probability of getting an odd. Okay, now let's talk about A given B. Now let's really get into these new terminologies, right? We would write this as the probability of A given that B has happened. Okay, but let's consider what are the possible outcomes given that B has happened. This sort of resets our sample space, right? It's no longer every roll of the die. We know the outcome was less than 4. That's our world now, right? It resets our world. So we know there is only B. There is only outcomes less than 4. So that's our new sample space, right? Like, how many ways is it possible to be less than 4? There are 3 ways of doing that, and those are now the only 3 ways we are considering. That is what given B means. It means, look, maybe it was possible for it to be more than 4 before, greater than or equal to 4 before. That's not what's happening now. We know for a fact it is less than 4. Now what is the probability of A? Now what is the probability of getting an even number? So of those, of the ones less than, you can just ignore this. It's gone, right? Like, this is the only thing that we're considering now. Of those, what's an even number? How many even numbers are there? There's 1. There's a 2. That's it. That's the only one. So when we are calculating A given B, there are now 3 options, and only one of them is even. This is 0.3 repeating, aka 33.3%. Oh, what about B given A? Does it change if I reverse the order? In general, yes. In general, B given A and A given B are not the same thing as one another. Let's consider now. It says that it's an even number, right? Given A, right? So that means now our sample space is just the evens, 2, 4, and 6. Right? This was our A, as opposed to B, right? Which was 1, 2, and 3. And so now what is the probability of getting a B, given that we are only talking about these 3 values from A? Those are the ones we have to pick from. Well, 3 is now the total number in the bottom. And A is so A is the number in the bottom, right? The 3 total outcomes from A. And B, what is B? It's the outcomes less than 4. How many of these are less than 4? Just this one. Just this one. So in this case, it did wind up being the same as A given B. That's okay. It's not that they're not allowed to be equal, but I will warn you, they need not be equal. You can't calculate one and think you have the other. Let's say A and B. Right? A and B. What is the probability of A and B? Well, in this case, we're still talking about the total number of possible rolls as being 6. We haven't reduced it. We don't know anything. We don't know if A or B happen. We just want to know what's the probability that they both happen simultaneously. So we ask what's in their intersection, right? A intersect B is literally just going to be the 2. It's actually T, right? There's only one way that happens. What about the probability of A or B? Well, okay, this is their union. What is A union B? Well, their union is 1, 2, 3, 4, 6. There are 5 options. And so 5 out of 6. Which, let me give a decimal for that. That's 0.83 repeating, or approximately 0.8333. 83.32%. Now we have a complement, A or not B. Okay, so first of all, what's not B, right? Well, B was 1, 2, and 3. The total sample space is 1 to 6. So the remaining guys that aren't in B but are in the sample space are 4, 5, and 6. And then A union with not B is then 1, 2, 3 from my, 2, 4, 5 from my A. 2, 4, 6 from my A. But there's already a 4 and 6 in there, so we're really just adding 2 to this set. And then we say, well, what is the probability of those? Well, what's the cardinality of this set? How big is it? How many things are in there? There are 4. There's 4 things in there. There's 4 ways that you could be either A or not B. And of the 6 total possible ways, we get 2/3. And what about event I? The outcome is a 7. What is the probability of I? How many ways are there to roll a 7 on a 6-sided die? None. None. There's no way to roll a 7. So the probability of that happening is 0. 0 is an allowed probability. And in general, if this is an impossible event, then the probability is 0. For finite events, it goes the other way too. If the probability is 0, then the event is impossible. But that is in general not true, especially not when we start dealing with continuous probabilities. But let's just say that the probability of a impossible event is always 0. That is true. Any impossible event has a 0% chance of happening. So I'm going to reload the board real quick because it apparently had a little bit of an issue there. Let's make sure everything is still locked. Yes, and let's zoom back in. So now we want to talk about these new terms: independent, mutually exclusive. What does this all mean? Right. So for independent, this is going to relate to our given conditional probabilities. Right? If I want to say that 2 events are independent, then really what I am saying here is that the probability of A is equal to the probability of, well, this is actually should follow under the how do I prove this thing. To prove this, we either demonstrate that probability of A is equal to the probability of A given B, or that the probability of B is equal to the probability of B given A. By Bayes' theorem, if you prove one, you've proved the other, right? You don't need to do both of them, you just need to do one or the other exclusively. You can do it both, but I mean, to show that if one of them is equal, then the other one will be equal too. And so what does this mean? It means knowing A has happened does not change the probability of B, and vice versa. So if they are dependent, they are simply not independent. In other words, knowing 1 has happened changes are the likelihood of the other. And so what we would say here is, to demonstrate it, you need to neither demonstrate that the probability of A is not equal to the probability of A given B, or the probability of B is not equal to the probability of B given that A has happened. And so now we're going to talk about kinds of sampling. So in sampling with replacement, the idea is that we draw observations from a sample space, let's just say we draw observations from the same sample space. In other words, repeating values, or observations, outcomes, is okay, is allowed. On the other hand, if we sample without replacement, we are removing each outcome from the sample space as we go. Think of drawing cards from a deck of cards. When I draw a card, once I look at it and say, aha, I've got the King of Hearts, I'm not drawing another King of Hearts, not if this is a fair deck, right? Not if there's only one King of Hearts in there. If I draw that and go to draw a second card, I know with 100% certainty I'm not going to draw the King of Hearts on the second time. So this is where repeated outcomes are not allowed. Right? We draw, we take a sample, we take an outcome, and once we observe that outcome, we will not observe that outcome again. Important note: always show two or more. Always assume that two or more events are dependent, unless you can show otherwise. Being equal is pretty special. Being not equal can happen in a lot of ways. This equality can only happen one way. So the generic situation is that things are dependent. Now, that's not to say that it doesn't happen an appreciable amount of the time. If I roll 2 die, those are usually independent. They don't have anything to do with each other. One roll doesn't tell me anything about the roll of the other die. So let's go on to the example here. It says, in a particular college class, 60% of the students are female. 50% of the students in the class have long hair. Okay? 45% of the students are female with long hair. Of the female students, 75% have long hair. So let L be the event that a student has long hair, F the event that they could be female. One student is picked randomly. Is being female and having long hair independent? So we know the probability of being female. It is 60%. 60% of the class is female. And then we know the probability of having long hair. Let's call that P of L. That's 0.5. And we know the probability of both of them happening. It says the probability of the students that are female and will have long hair, so F and L, we know this probability is 0.45. It says of the female students, 75% have long hair. So the probability that you have long hair given that you are one of the female students. See, of the female students, we're only considering that world, given female now. Of that, that's 75%. 75% of the female students have long hair is another way of saying that given that you are female, the probability that you have long hair is 75%. And it says one student is picked at random. Are these independent? Right? Well, no. I mean, this is not equal to the probability of L. Right? We said that was actually 0.5. Right? And so that's it. That's the criteria. Because of this, they are not independent. If you tell me that the student is female, it changes my perception of how many of them have long hair. If you tell me that they have long hair, it changes my perception of whether or not they might be female or not. Right? Just for this class and probabilistically speaking. Okay, let's look at this example. It says a box has two balls, one white and one red. Okay, we select one ball, we put it back in the box. We select a second ball. So this is sampling with replacement. We replace the values back in the box, right? And so each draw, each experiment is identical, right? It's taking place over the same sample space with the same probabilities. Let T be the probability of getting a white ball twice. Let F be the probability of picking the white ball first. And S the event of picking the white ball on the second drawing. Okay, that's fine. So the probability of getting the white ball twice, P of T. This means that you pick the white ball first. So F, white ball first. And you picked it twice, S. So what is that probability? Well, it's probability of F times the probability of S given F. This is a simple classical example. There's two balls, equal probability of each. So the probability that you select a white ball in the first time is 1/2. And then the probability of S, given that you selected a white ball, the probability of selecting a white ball the second time, given that you did the first time. Well, wait a minute. You put the ball back in, shook that box around, right? It doesn't matter that you picked a white ball first. There's no difference between this and the probability of S, just picking a white ball in the second time, because we're dealing with sampling with replacement. It's put the balls back the way they were, and so that resets our world back to the case where there's just one ball, which is white, and one ball, which is red. So this is another 1/2. And then the probability of these is 1/4. 1/4 of the time you will pick the white ball twice. What is the probability that you draw the white ball twice, given that we already drew the first ball and it was white? Okay, well, wait a minute. All we have to do then is draw a white ball the second time. So these are equal probabilities. Right? Are T and F independent? No, they're not independent, because T given F is different than just probability of T. The probability that you draw the white ball twice is 1/4 of the time. You look at the possible outcomes, right? White ball, red ball, red ball, red ball, red ball, white ball. And this is our first, this is our second draw. And then white ball, the desired outcome, right? This is our event T right here. Right, okay, well, if I know that we drew a white ball If I don't know anything, right, then there's 4 outcomes and one of them is white, white. That's why this is a quarter. On the other hand, if I know that we drew a white ball the first time, that eliminates these 2 possibilities. Then what's the probability of drawing a white ball? Well, now there's only 2 options. That's why it's 1/2. So no, if I know that I got a white ball the first time, it changes my understanding of the odds that I'll draw a white ball twice. Are S and F mutually exclusive? Well, did we talk about mutually exclusive yet? No, it's under here, so that's not very fair. Let's put that off until we answer what the heck those 2 things are. And what about independent? Right? What's the probability of drawing the white ball first? It's 1/2. What is the probability of drawing the white ball first, given that we drew? Well, let's even do S, because it's a little hard to say given when we're talking about these time things and something happens in the past. So let's say, what's the probability we draw a white ball in the second time? Well, since we did replacement, this is just 1/2. What's the probability that we give a white ball in the second time, given that this is drawn white on the first time? Again, as I kind of alluded to up top, this is no different than the probability of S. You draw a white ball the first time, great, awesome, cool. You replaced it back into the box though, right? So it resets the world to look exactly like it did on the first draw. So they don't tell you anything about each other. These 2 are independent. So mutually exclusive means they cannot happen simultaneously. In the previous example, you couldn't draw a red ball and a white ball for your first draw because you're forced to choose between one and the other. This says you draw a white ball on the first time. You draw a white ball on the second time. Can those happen together? Yeah, there's a situation where those happen. Like you draw a white ball, you put it back, and then you draw a white ball on the second time. Yeah, those can happen together. So no, they're not mutually exclusive because they can happen together. Right? We would say that the probability of F and S is non-zero, right? There is a situation, 1/4, where that could possibly happen. What does mutually non-exclusive mean? That they can happen simultaneously. So we have to assume that they can happen simultaneously, unless we can demonstrate that something is impossible. Like, for example, A and A complement are mutually exclusive. That's like a fundamental assumption, law of the excluded middle, if you like, right? That's something which will always be the case. It is always the case that a set and an event and its complement are mutually exclusive. Example. Consider the experiment where 2 fair coins are flipped at the same time. Let T be the event that tail was obtained, H be the event that heads was obtained. TH is tails is first and heads is the second coin, and TT, tails is obtained on both flips, and so forth. So they're going to indicate a single event for just one of the flips by T or H, and then the order of this is going to tell me about whether or not the first or second coin was flipped. Let's make a little chart here. Also, let's get into a new color. Let's say that we have coin 1 and coin 2. I like that a little bit better than first and second coin because we really don't have to flip them at 2 different times for this to make sense. So either this could have tails or it could have heads. Either this could have tails or it could have heads. So to list all the options, I need to list all the ways that one could have heads and tails separately, that I could get coin 1 as heads, coin 2 as tails, or that they are both heads. Okay, so these are all the possible outcomes in my sample space. What is my sample space then? It's this set: tails, 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 heads, heads, tails, and heads, heads. And you could say 2 fair coins are flipped at one time, or you could say 1 fair coin is flipped twice, right? Either one of those are going to have the same kinds of outcome. Okay, what is the probability of F? At most 1 tail. Well, how many have at most 1 tail? 3 of them. 4 total outcomes. What's the probability that you get both tails? All tails. Well, there's 1 outcome where that is true out of 4 possible outcomes. What is the probability of all heads? Well, the same thing. There's only 1 all heads probability out of 4 possible outcomes. What about D? More than 1 tail. Okay, well, there's, again, only 1 way that that's possible, which is by getting 2 tails. J, heads on the first flip. There are 2 ways that that is possible out of a total of 4 outcomes. So we would say that this is 2 out of 4, aka 1 out of 2, aka 50%. K, at least 1 tail. Oh, I misread the first one. I beg your pardon, right? At most 1 tail could have 2 different ways that could happen. Or excuse me, right? 1, 2, and then this is at most 1 tail. Okay, so it is 3. What am I? Oh, I see. So then at least 1 tail is sort of the not the complement of that. That's what was getting me a little confused. At least 1 tail means this one, or hey, 2. 2 is just as good. That's at least 1. 2 is at least 1, right? It's actually more than 1, but at least means greater than or equal to. I know that's a little silly, but at least means greater than or equal to some number. So this is actually all 3 of these options, so we have another 3 out of 4 probability. Which pairs of events are mutually exclusive? Well, let's think about if we can do both of them. Can I do at most 1 tail and all tails? No. Right? F and G. Those are mutually exclusive because if I do all tails, I have 2 tails, and that is more than 1 tail. So those 2 cannot happen simultaneously. If I get 2 tails, aka all tails, then my probability of getting at most 1 tail is 0. What about F and all heads? Well, if you get all heads, you do also have at most 1 tail because you have 0 tails. So that's fine. F and I, more than 1 tail. Those you can't get more than 1 tail and at most 1 tail, right? So F and I are mutually exclusive. At most 1 tail and heads on the first flip. Well, yeah, of those, there's both of those I get at least 1. So yeah, F and J can happen at the same time. And what about F and K? At most 1 tail and at least 1 tail. Well, if I get 1 tail, which happens 50% of the time, I'm good for both F and K. So they can happen together. All right, let's do the other comparisons, G and H. Right? Can I get all tails and all heads? No, you can't get all tails and all heads. What about all tails and more than 1 tail? Yes. What about all tails and heads on the first flip? No. If you get heads on the first flip, you can't get all tails. You got a heads. What about all tails and at least 1 tail? Yeah, you could do that. What about C? All heads and more than 1 tail? No, you cannot get all heads and also more than 1 tail. That wouldn't work. Then you wouldn't have all heads. What about all heads and heads on the first flip? Totally could do that. What about all heads and at least one tail? No, you can't do that. You can't get at least one and then have all heads, at least one tail, but some of them are but all of them are head. No, that doesn't work. Those don't go together. So H and K are mutually exclusive. What about I and J? More than one tail and heads on the first flip. No, there's only two rolls. So if you get heads on the first flip, you can only get at most one tail. So I and J are mutually exclusive. What about I and K? Can you get more than one tail and at least one tail? Yes, two is at least one. So those two go together. Finally, what about J and K? Can you get heads on the first flip and at least one tail? Yes, you can, right? Here's the situation where that's true. Okay. So here's where I think they really do suss out the actual formula for these two probabilities. So I'll just list them here, right? This is going to be the probability of A times the probability of B given A. And that is equal to the probability of B times the probability of A given B. If A and B are known to be independent, well, then both of these givens are just equal to the respective probability of B or a probability of A. So if that's true, then in either case, we're going to have probability of A times the probability of B. If they're independent events, then the probability that they happen simultaneously is just the product of their probabilities. Finally, what's the addition rule for OR probabilities? Okay, well, this is going to be the probability of A plus the probability of B. But this actually is too big, right? That could be greater than 1 even. The problem is that we haven't taken into account what if it's both? Then when you counted all the ways that A could happen, you included perhaps some B's happening. And vice versa. If you counted all the ways that B could happen, maybe you're double counting some of the A's. And the only way that you can omit that double counting is by taking away those things that we would have double counted. That is to say, when they do happen simultaneously. So this is a formula. It's actually part of a family of formulas called inclusion-exclusion. But it's a formula which tells you how to correct the probability for A or B in the case that we don't know if they're mutually exclusive. We don't know that the probability here is 0. Now, I bet you on the next page, they're going to mention something about that. They're going to mention if A and B are known to be mutually exclusive, right? Well, if they're mutually exclusive, then this means that they cannot happen simultaneously. So what is the probability of A and B in the event of mutual exclusivity? 0. Remember, mutually exclusive means A and B is impossible. And the probability of an impossible event is 0. And so then you just get their sum. And this harkens back to the idea of classical probability just being a sum of the outcomes. If the outcomes are distinct, right, then the event that has to do with some number of outcomes, the probability of that event is just the sum of the probabilities of the outcomes pertaining to that event, right? Because we're assuming outcomes are distinct, right? You don't have an outcome where there is some kind of overlap between the two outcomes, right? We're just assuming that could happen between events. Okay, Carlos plays soccer. He makes a goal 65% of the time he shoots. Carlos is going to attempt 2 goals in the next game. A is the event that Carlos is successful in his first attempt. That's 65. B, that he's successful in his second attempt, is 0.65. He tends to shoot in streaks, though, which means that if he makes the first goal, he's probably going to make his second goal. That's what it means to shoot in streaks, right? So they've said then that the probability that he makes the second goal, given that he made the first goal, right? So that's the probability of B given A is 90%, right? And they contrast that with just the simple probability. What if he shoots a goal? In both cases, 65%. So what's the probability he makes both goals? That's the probability of A and B. That's equal to the probability of A times the probability of B given that A has happened. So that's going to be 0.65 times 0.9. 0.65 times 0.9 is 0.585. What is the probability that Carlos makes either the first goal or the second goal? Okay, so the probability that A or B happens is going to be the probability of A plus the probability of B minus the probability of A and B. And that's going to be equal to 0.65 plus 0.65. Notice that's too big, right? That's too big. That would be 1.25, and that's not a valid probability. But what we're going to do now is subtract from that the thing that we've overcounted, the chance that he actually does both A and B. And if we carefully do that, we get 0.715. Are A and B independent? Well, I don't know. Is the probability of B, which is 0.65, equal to the probability of B given that A has happened, which is 0.9? No. Right? We know something about the probability that he shoots a second goal given that he scored the first one, and it's 90%, not 65%. So, no, that changes. Are A and B mutually exclusive? Well, I don't know. The probability of A and B happening turned out to be equal to 0.585 and not 0, right? So that means that no, these are not mutually exclusive events. There's nothing that keeps him from scoring a second goal if he scored the first goal. In fact, it's more likely that he's going to score. Right? It goes up from B. Well, yeah, that's all I have to say about that. No, if the probability of A and B is non-zero, then A and B are not mutually exclusive. In a group of 20 college students, 7 are sophomores, 13 are freshmen. Let S equal the event that a selected student is a sophomore, and F be the event that they are a freshman. So notice that those are mutually exclusive. You cannot be both a sophomore and a freshman. You cannot be in your first year and your second year at the same time. So what do they want? What's the probability that they're both freshmen? Now, keep in mind, when we select from this group of 20 college students, what we are doing is selecting without replacement, right? We're going to take 2 students. We're not going to put a student back. We're taking 1 student, and then we're taking a second student from that group of 19 that are left, right? This is drawing without replacement. So this changes the world, right? When we say, when we look at given probabilities and we draw without replacement, things change, and it's very difficult for things to maintain independence. Let's look at that. So what is the probability? Let's say that the probability that F1, the first student, is a freshman, and F2, the second student, is a freshman. Okay, so what's the probability that the first student is a freshman times what's the probability that the second student is a freshman given that the first one was a freshman? Let's be very careful about this. The first term here, right? The probability that the first student is a freshman. There's 13 freshmen, there's 20 college students. So this is 13 over 20. Now, given that we've drawn a freshman, there are only 12 freshmen left. And we are only drawing them from 19 remaining college students. So this second probability, the second freshman, is 12 possible freshmen remaining over 19 total students remaining. And taking this product, right, what is 13 times 12 divided by 20 divided by 19? 0.4105, approximately. So now, what about the first student is a freshman and the second student is a sophomore? So we'll say that's the probability that the first student is a freshman and the second student is a sophomore. Well, that's the probability that the first student is a freshman times the probability that the second student is a sophomore, given that the first student was a freshman. You can't, right? We have to be cautious about how we've changed the world by selecting the first student being a freshman. 13 out of 20, same as before. But now there are 7 remaining sophomores because we didn't draw one on the first round. We drew a freshman out of 19 remaining college students. And so that is going to give us 0.2394 approximately. Well, rounded, that's going to be 0.2395. So now to talk about marginal probability. Marginal probability is going to be the probability of a single event occurring. Independent of the other events. And the reason it has this name marginal is because traditionally what we would do in the quote unquote margins of a table, which are the values, over here on the side, is we would write the sums, right? We would write the sums of each column and the sums of each row to try to get a handle on how each variable sort of stacks up. How many total men? How many total females? How many total left-handed people? Right. So if we take a look at, for example, let's say, let's start with men. Right. So of these 100 individuals, they happen to all be either male or female. And of them, the ones who were male are 43 right-handed people and 9 left-handed people. So that's a total of 52 total males. Those identifying as female are 44 right-handers and 4 left-handers. That's 48 total females. And what about the column sums? Well, that would tell me the total number of right-handed versus left-handed people. So the probability of being right-handed, or the total number of people who are right-handed is 43 plus 44. That's 87. And how many left-handers? There are 13. And notice both of these, either this new row sum or this new column sum, both would give me 100 total people. It's important that either of those would add up to be the total. This has to do with the associativity and commutativity of addition, but it should be kind of obvious. Now, to talk about the marginal probability, so marginal probabilities are things like this. These first 4 are marginal probabilities, and we call them that, these single event probabilities, because we're going to look to the margins for the number of people that satisfy that event criteria. There are 52 males combining the right-handed and left-handed situations, but we don't care about that. We just care about how many are males. There are 52. What about females? Same idea. There's 48. And where did we go to get this information? The margins. That's why this is the marginal probability. What about probability of being right-handed? Well, there are 87 right-handers. What about the probability of being left-handed? There were 13 left-handed. What's the probability of being male and right-handed? All right, so we do have a formula for that, but let me just put it to you like this. We also know how to find the male right-handed people. It's right there. It's right there. It's in the table. If they give you a table, they're basically laying all of the information out for you right there. There are 43 right-handed males. That's what we're looking for here. And so that's 0.43. What about female and left-handed? Female and left-handed. Well, that's right here. This is the intersection of female and left-handed. There are 4 of them out of a total of 100. I want to just show you real quick, before we kind of push this too far forward, that our formula really does work, even in the case of these tables, right? We have a formula, right? It says that this is F times the probability of F given L. But maybe I'll just hold off for just a moment, because we're going to calculate the probability of the givens in just a moment. And we'll see that those two are actually going to be equal. The product that I've shown and the 4 100ths that we get by just going straight into the table and pulling out that value, which satisfies both female and left-handed the criteria. Let's keep going. What about male or female? Well, in this case, that spans the total number of options. You can either be male, or you could be female. And on this table, there's no NBs. You can't be both. You can't be neither. So male and female. But according to this table, this is mutually exclusive. Well, wait a minute. That means this sums all of the possibilities. That means that this is 52 out of 100 plus 48 out of 100. That's everybody. So that is 1. And in this case, you must be either one or the other. What about female or left-handed? Female or left-handed? Well, or conditions, that's all of the females, but it's also all of the left-handed people. So that's all of these ones here. Everybody in this kind of L or, kind of hockey stick shape that I've drawn here, everybody in here, these are all of my females that are left-handed. Females or you are left-handed, right? We're including these 9 left-handed males, these 4 left-handed females, and these 44 right-handed females, and saying female or left-handed, right? So this is actually 44 plus 4 plus 9 over 100. That's 48, 57, so this is 0.57. But wait, we had a formula for that too. We did. Does it work? I mean, or did we just abandon our formula by going straight into the table and counting all these values? No, we didn't. We didn't. The formula will recapitulate this, right? Probability of female or left-handed is equal to the probability of female plus the probability of left-handed minus the probability of female and left-handed. And we saw that there were, how many kinds of females? Well, 44 plus 4 of them, right? Over 100. That's how many total females there are. I know that's 48, but watch this. Plus, I've got how many left-handed people? Well, there are 9 and there are 4 for males and females respectively. But wait a minute, you can see what I've done. I've counted the 4 twice. Well, that's no good. I only wanted to count it once. So what's the deal with this double counting? Wait, I'm going to get rid of that. I'm going to get rid of precisely that, the amount that I've double counted. And that's why it disappears. And that's why this formula works. Okay, here's another formula for another symbol for the complement. In this case, that's the probability of being female. But I'll just say that's 1 minus the probability of being male, because actually that's a little bit more general and, to be fair, more accurate. What is 1 minus 52 over 100? It's 48 over 100, or 0.48. All right, now let's do some of these given probabilities. Let's see how that looks on the table, right? What if I said the probability of being right-handed given that you are male? So the way that I like to think about given male, right, is that you have omitted all of the information that isn't involved in being male in this table, right? You're just now looking. This is it. If you said given male, this is our world. This is where we're staying and playing. And so what's my new total? It's 52. Now there's 52 total individuals. It resets what the denominator will be when we choose given some information. And of those, how many right-handed people are there? Well, now there's only these 43 because we're only looking at the males. So what is my probability here? It's going to be out of 52 total males, there are 43 who are left-handed. And we could carry out that probability. 43 divided by 52, and we get something like 0.8269, approximately. And what about female given left-handed? Well, again, we are now resetting the world so that only left-handedness is considered. That's it. This is it. We're just saying we've been given left-handed individuals, so we're not going to look at any of the right-handed information. We know they're left-handed, so this is our world. And in that case, right, I have for given L, I have a total of 13 left-handed people. And how many of them are female? 9. And 9 out of 13 is 0.6923, approximately. And we'll go back to the original thing I wanted to mention about these givens over here. But first, let's do given. Let's see what happens when we switch them. Like what's different, right? Well, your probability given female, if we look at just the females, right, then there's 48 total females. And of those, how many are left-handed? 4. And this is approximately 0.083 repeating. Actually, that's exact. Let's say that's approximate. Now, let's take a look at this thing I wanted to mention, right? How does this formula for and relate to the givens, right? Well, let's write out what they would be. How many different ways are there to be female in this chart? There are 48 different females responding, so that's 48 out of 100. And then what's the probability of being female given that you are left-handed? Hang on. Maybe I've made a mistake here. Let's see, because something should cancel nicely. I know what to expect. This should be 4 out of... Oh, because I've written my formula wrong, of course. Yeah, let's fix that, because that's not going to make any sense. That's not even true. So this is L, right, given F. That's it, right? We need A times the probability of B given A. I had the order wrong. So probability of female is still 48 over 100. And then the probability of L given F. So L given F is 4 over 48, because now the females form my denominator while they form the numerator of the first one. But hey, look, they cancel. That does give me exactly what we had before for the and probability. So just go looking at the value in the table and saying out of how many total, or using the formula for and probabilities in terms of a marginal probability and this conditional probability. Both ways are equally acceptable. This way, I think, is a little bit easier if you have a table. Okay. Looks like we're off the edge of the map. I believe that means we've come to the end of the first line here. All right, so let's circle on back to the beginning here and continue on. I will try to get through this entire packet in the 2.5 hours that we would normally be meeting. Okay, so here we have a partial table. It says this contingency shows a random sample of 100 hikers. Okay, well, thanks for letting me know, Jimbo, that this is 100 hikers. And from there, I could probably start filling in different amounts, right? If this row sum is 45 females, how many of them preferred hiking in the mountains? Well, 45 minus the ones that hike on the coast, minus the ones that hunt in the desert, are 11, right? This number would make the 45 total when we sum them. And now, what about the total number of people that go to the mountains? Well, that's 25. And then this says that the total number of coastal hikers, desert hikers, and mountain hikers also must be 100. So 100 minus that 25 minus that 41 tells me how many people go on the coasts. It's 34. And then now we can fill out this total, right? If there's 41 total desert hikers minus the 16 females, there must be 25 males. If we have 18 people on the coast and that are female hikers and 34 total, then 34 minus the 18 gives me 16 males. So in general, we can complete a contingency table if we can figure out what goes in each spot to make a total row sum or column sum. Kind of like a little mini baby Sudoku. Okay, and then this is going to be the exact same kind of thing. So I'm going to move through it a little bit faster than the last one. How many people? What is the probability of being male? Well, there's 55 total males out of 100. How many people are female? Well, the probability is 45 total females out of 100. What about female given that you're a coastal hiker? Well, if I just look at the coastal hikers and I don't look at anything else, there's 18 females out of a total of 34. I'll let you guys find out the decimals on your own. What about probability of male given that you're a desert hiker? Well, of the desert hikers, of which there are 41, there are 25 males. What about the probability of female and desert hiker? Of that kind of people, there are 16 out of the total of 100 that we have in the sample. What about C and M? Okay, so we intersect those two, and that's 16 in that cell divided by 100 total. What about female or mountain? Okay, well, how many females are there? There are 45. How many mountain hikers are there? There are 25. That has overcounted precisely by the number of female mountain hikers, of which there are 11. So we take the sum, we minus the and condition, and we divide by 100. What about or? Oh, well, what about C or D? Coast or desert? Well, keep in mind, you cannot be coast and desert. You had to pick. Is your favorite one the coast or is your favorite one the desert? You don't get both. So these are mutually exclusive. And so in a mutually exclusive event, we just have to worry about their sum. That's 34 coastal hikers plus 41 desert hikers divided by 100. What about the probability of not female? Again, that's I would prefer to think of that as 1 minus the probability of female, just so maybe eventually I can slip some quasi weird gendered nonsense in at you. But in this case, it's also equal to the probability of males because they're saying there are males and there are females, and that's the total, and they don't intersect, and there is no third option. What about the probability of not being a coastal hiker? Well, how many different ways are there to do that? There's 41 desert hikers, there's 25 mountain hikers, and then we're dividing that by 100 total. Are mountain hiker and desert hiker independent? No. No, they're not. Because if I tell you what's the probability that they said that deserts were their favorite given that mountains were their favorite, it's 0. What's the probability of hiking in the desert? Well, how many desert hikers were there? I forgot. There's 41, right? So this is 41 out of 100. So those aren't equal. Why is this 0, right? Because they're mutually exclusive. You cannot be a desert hiker and a mountain hiker and have those both be your favorites. I get that maybe you like them both equally, but in this case, we were asked they have to pick. They have to pick desert or mountains exclusively. And so, given that they said mountains, what's the probability that desert was their favorite? 0. They said it was mountains. They said the favorite was mountains, so it cannot be deserts. Are desert and coastal hikers mutually exclusive? Yeah, they totally are. You cannot be both, right? In general, what we'll usually do is have these columns and these rows be mutually exclusive. So a tree diagram is something called a tree graph. This is not your normal graph that you graph a function. This is a collection of nodes and edges which connect the nodes, also sometimes called vertexes. And the only rule to make something a tree, it doesn't really even have to go in one direction, although we're going to have it be a rooted oriented tree. All that has to be necessary is that it cannot actually have a cycle. It cannot have a place like this where we now have sort of a loop. It has to have sort of a branching process, and the branches, much like the branches of a tree, right, don't grow back together again. In Florida, we have a lot of banyan trees, and there's some anastomoses where the things do grow back together again. We mean most trees don't have that problem, right? Most trees, once they branch, they don't unbranch again. They keep forking. And that's the idea of not having any cycle. They don't merge back together again. They just keep branching. And if you do this, you can sort of imagine taking the whole thing, flipping it upside down, shaking it a little bit until all the sticks sort of pointed downwards. And you would get something like these forked diagrams that they're trying to show you here. So, what is a tree? A tree is an acyclic graph. I will actually omit that definition. So it's going to be a series of forks, shall we say, that do not merge. And when we're talking about tree diagrams, that's what a tree is. What is a tree diagram? Where each fork indicates some kind of event stage where we're going to look at perhaps 2 or more different outcomes that could happen. So, where each fork represents some experiment let's say some stage of the experiment. And at that stage of the experiment, right, we have to choose an outcome. So let's look at an example and see, because this is a depiction of how we could represent all of the possibilities in doing a series of draws or experiments on a single set. In an urn, there are 11 balls. 3 balls are red, 8 balls are blue. Draw 2 balls, one at a time, with replacement. So again, with replacement means you put that ball back in the urn before you select the second ball, and that means there's always going to be 8 blue and 3 red on each draw. So you could imagine these as sort of like world lines. When I draw the first time, I have 2 options. Either I'm drawing red or I'm drawing blue. I'll try to color code this. Maybe that'll be fun. Right. So here's the red possibility, and on the other side, maybe I draw a blue ball instead. Possible. And so they will say which of those we are going to have as the node. Right. They'll represent what outcome that was as the node of the next part of the graph. So did you draw blue? Okay, then there were 8 ways to do that. Did you draw red? Okay, well, there were 3 ways to do that. And then we draw a second draw. So on the second draw, maybe you drew a red. Or in the blue region, maybe you drew a red here. Or on the second draw, maybe it's possible that we drew a blue ball after we drew a red. Or maybe we drew a blue ball after we drew another blue ball. Since we did replacement, nothing's really changed, so we still have 8 blue balls and 3 red balls in either one of these 2 outcomes. So now when we talk about this as a total experiment, so we're considering this to not be a series of experiments, but this is one experiment. It's drawing twice. It's got stages. At different stages, different outcomes are possible. What are those outcomes? Well, here they are listed. Either a blue for the first one and a blue for the second one, a blue and then a red and then a blue, which is different, and then a red and then a red. So what is the size of the sample space? Well, how many different options are here? There's 4. 4 total options about how we could have selected the balls. Calculate the following items. Red, then red. Okay, so what they mean here is the probability that the first ball was red, I'll write that like this, and that the second ball was red. Now, because this is replacement, we are replacing, these are independent from each other, right? I'm looking at the probability that the first ball was red times the probability that the second ball was red, given that the first ball was red. But actually, this part doesn't really matter, because by replacing the ball, I've reset it so that there's the same number of red and the same number of blue balls on the second draw. So nothing really changes between the 2 of them, and we can really just say, what's the probability of drawing a red ball? So this is just going to be the product of the 2 probabilities. What are those? So there's 3 red, there's 11 total, and then in the next draw, there's 3 red and 11 total. So this is 9 over 121. What about red, red, or blue, red? Well, you can't have both of them. Those are mutually exclusive events, right? You cannot have both blue, red, and red, red. Those are not the same. They are distinct from each other, right? So that means we don't have to worry about the minusing in the OR formula, and we can just take their sum. What's the probability of red, red? I'll switch back to red for that, sure. The probability of red, red is 3 out of 11 times 3 out of 11. Plus, what's the probability of blue, red? 8 out of 11 for that first draw for blue, and then 3 out of 11 Oops. For that second draw for red. And what is that total probability? Well, that's 9 plus 24. That's 33 out of 121. Red on the first draw or blue on the second draw. Okay, let's go up to our sample event and circle those things. Right? I've got red on the first draw. There's 2 of those. Blue on the second draw. I've got 2 of those. So is it just their sum? Well, no, because now blue on the second draw, red on the first draw have some overlap, right? Here's one that does both. So I could say I'm sorry, red on the first draw and, I misread that. I thought that said or. Okay, so red on the first draw and blue on the second draw. There's only one such option. Now, what's the probability of getting that option? Well, in order to do that, you had to have 3 out of 11 on this, and then 8 out of 11 to get this one. So let's just write this. This is the probability of getting red on the first draw times the probability of getting blue on the second draw. And that is 3 out of 11 plus, times, we're doing and probabilities, times 8 out of 11. So that's 24 out of 121. What about the probability of red on the second draw given blue on the first draw? Okay, well, if I go down that line, right, if we're given blue on the first draw, then we're only looking at this region. That's it. That's all we care about. It restricts my sample space. I'm no longer concerned about these. I'm only looking at these 2. And there's 2 options. Either you got red or you got blue. Well, there's only one way of doing that. There's only this 3 out of 11 now. That's the only way, if we know that we got blue on the first draw, that we're getting red on the second draw. So, to wit, this is 3 out of 11 only. What about the probability of double blue? Well, that's blue on the first draw and blue on the second draw. That's 8 out of 11 times 8 out of 11. Lastly, what about blue on the second draw given red on the first draw? Again, the given resets your world so that you're only looking at this region. We know that red is what we have. We know that these outcomes are now impossible. We got red on the first draw. What is the probability now that you get blue on the second draw? 8 out of 11. Okay, on to the next page. A litter of kittens is available for adoption at the Humane Society. They have 4 orange and 5 brown. A family comes and randomly selects 2 kittens. All right, there's no way that you randomly pick your kittens. I mean, I don't know what your criteria is, but you play with them first. And so what is so here we have a litter of kittens, 4 orange, 5 brown. So we have 4 out of the 9 kittens and 5 out of the 9 kittens are orange and brown respectively. Now notice, on the next round, we are selecting 2 kittens. You're not putting the kittens back and then plucking them up just to have fun. You're picking 1 kitten, and then that's out of the pool of selection. You've already picked that kitten. So that's why all of these denominators down here switch to 8s. And then we have given probabilities. So given that you've selected orange, there are different probabilities for orange and brown. Given that you selected brown the first time, there's different probabilities for orange and brown. So this is a little different. This is selection without replacement. What is the probability that both kittens are orange? Okay. Well, that's going to be the probability that the first kitten is orange. So we were talking about kitten 1 is orange. I'll put that as orange 1 and orange 2. Okay, well, that's the probability that orange kitten 1 is selected, and then the second kitten is also orange, given that we have selected the first kitten as orange. And now that we've doing this without replacement, this is a very important distinction to make. What is the probability that the first one's orange? 4 out of 9. And then once we're down this world, right, this is the only thing we're looking at now. What is the probability that the second cat is orange? 3 out of 8. Take that, get 12 out of 72 and continue. What is the probability that one kitten of each coloring is selected? Okay, well, there are 2 options for that, and they're mutually exclusive. You're either picking an orange kitten and a brown kitten, or you're picking a brown kitten and an orange kitten. So this is going to be written like this. This is equal to the probability of orange kitten first and brown kitten second, or brown kitten first and orange kitten second. So since we did something kind of like this in the first one, I'll just write out what those 2 would be. The OR condition means we're going to sum them. The AND condition means we're going to take the product of one and the given probability of the other. So this is going to be probability of orange. That's 4 out of 9. And then given that you selected that guy, now you pick a brown. Okay, that's 5 out of 8. Plus the probability that we do brown first, which is 5 out of 9, times now orange kitten, that's 4 out of 8. Hey, notice those are suspiciously similar, right? Okay, well, that's going to be 20 out of 72 plus 20 out of 70. That's 40 out of 72. What is the probability that the second kitten chosen is orange when a brown kitten was chosen first? Okay, well, if we just go into the brown kitten chosen first kind of a world, right, then that's this world, right? Given brown means just here. And then of those, what's the probability of getting an orange kitten? 4 out of 8. Right, so this is the probability of orange kitten second, given that brown kitten was chosen first. And that's going to be 4 orange kittens out of a total of 8 remaining kittens. What is the probability of choosing 2 kittens the same color? All right, well, that's going to be the probability of orange 1 and orange 2, or brown 1 and brown 2. And we could just spell that out. This is 4 out of 9 times 3 out of 8 plus 5 out of 9 times 4 out of 8. That's 12 plus 20 is 32 over 72. So a Venn diagram is a way of depicting sets. Sorry for the lag, where members are inside of circles representing the sets. So here we have a set A and a set B. And the idea is that whatever's inside here is the members of A, including the stuff in the middle. But the stuff in set B is also inside its circle, including perhaps this middle bit as well. So this, right, in between them represents where we might have both A and B. So let's write down what they have. So here they have some listed events. They have green, blue, and purple. Okay, so green, blue, but notice blue is also in B, so I'm going to put him here, and purple. And then set B has red, yellow, and blue. And they say, we want a constructive Venn diagram that shows these sets. Well, let me color code a little bit more. What is set A? It's this set here. What is set B? It's this set here. What is A union B? That's this whole set, including everything that's in both of them. This kind of peanut shape. What about A intersect B? Yeah, orange should be fine. Oh no, I used that for B already. Let's use maybe pink. That is depicted right here. This is what they have in common. And then this one's nice. This is what is the complement of their union? So I will indicate that with what's another color I have remaining? Rainbow? Rainbow? Everything outside the set is the complement of the union. So that's this fellow right here. Okay. Let's say we have these two events. We have A, tails on the first coin, B, tails on the second coin. So let's list the possibility of flipping two fair coins. We might have tails and tails. We might have tails and heads. We might have heads and tails. We might have heads and heads. That's all four possible options flipping two coins. And so which of these fall into A, tails on the first coin? Well, tails and tails, but that also falls into the category of B, which is tails on the second coin. Here I might have heads and tails. What about tails on the first coin? Yeah, that we also have tails on the first coin and heads. That would fall in here. And then it says, well, what about the last option, heads and heads? Well, that would be neither having tails on the first one nor having tails on the second one. So our this conglomeration here is S. It's tails tails, or tails heads, or heads tails, or heads heads. And then what about A? Well, that's just the set where tails is on the first coin, so tails heads, or maybe tails tails. What about B? That's heads tails, or also perhaps tails tails. What about A union B? That is tails heads, heads tails, or maybe tails tails. What about the complement of their intersection. Wait, I thought the first one said complement of their union. Did I misunderstand that? No, they did. It said complement of their union before. Okay, I got a little nervous there. What about complement of their intersection? Complement of their intersection. That's a little different, right? I mean, here's the intersection. It's everything inside this. What's its complement? It's everything outside of that. Everything outside of that. So what is the complement of the intersection of A and B? Well, the intersection is just tails, tails. So we're talking about everything else. We're talking about heads, heads. We're talking about hails, heads, heads, tails, tails, heads. Can't roll hails, heads on any coin that I'm familiar with. Okay. And I think that's all they want. Now, the counting rule is a way of saying that if I have 3 different choices to make, or say n different choices to make, with m options in each one, then I'm looking at the product of the number of options in each case. Let me try to write this down. The total number of outcomes in an experiment with n decisions amongst, let's say, m sub I options on the ith decision is their product. So m1 times m2 and so on, all the way up to mn. I think a graph is or a picture is probably nice to suss out what the hell that means. If I have, 3 options for socks, 4 for shirts, 5 for pants. How many different outfits? That's the idea here. Well, for every single pair of socks you have, there's 3 different ways we could go, 1 for each pair of socks. Then each one of these splits again when I choose my shirts. There's 4 different options there. And each one of these splits again when I choose my pants. And it doesn't matter what order I do this in. Each one of these branches splits the same amount. And so I have 3 times 4 times 5 different options. That's 60 different outfits that are possible amongst these 3 options of shirts, socks, and pants. And so the way that we might use that is to talk about how many different ways there are to have an outcome in a certain experiment. For example, it says you have 3 tosses of a coin. Well, a coin can be heads or tails. And then I toss it again, and it splits again. And I toss it again, and it splits again. So I multiply by 2 each time because I have 2 options for each layer of the experiment. So for 3 tosses of a coin, that would be 2 times 2 times 2, or 2 to the 3rd, which is 8. If you have 4 tosses of a coin, that's 2 to the 4th. aka 16. But this is, again, just this kind of product counting rule. At each layer, you increase the number of options that you have by 2, so you're multiplying by 2. We're going to consider the factorial as the number of ways. So we say n factorial is equal to the number of ways to order n things, where n is some non-negative number and is a whole number. And what does this look like? What is the actual formula here? How do you calculate n factorial? Well, in the case that n is equal to 0, there is only one way to order no things, which is just to not do it. There's only one way to order one thing as well. Both of those are 1. And in the case of, say, n greater than or equal to 2, we would take and multiply n times n minus 1 times n minus 2, and so on, all the way down until we got to 2. Could you multiply by 1 as well? Yeah, absolutely. But, it's really not going to matter because multiplying by 1 doesn't change anything. So, for example, what is 5 factorial? 5 factorial is 5 times 4 times 3 times 2 times 1, I guess. That's 6 times 20, that's 120. Consider a group of 10 marathon runners. How many different orderings exist for the first place to the 10th place of the race? Okay, so 10 factorial. You have 10 options for the first place winner, and then of the remaining runners, there are 9, so you have 9 options for the second place winner, and then 8 options for the third place winner, and 7 options for the seventh place winner. Fourth place winner. Shoot, I lost track. How do you do this? 10 times 9 times 8 times 7. Wait a minute. This is heinous. There must be a button for this, right? There is, right? Let's grab our calculators, right? And we would go to math and down to probability, PRB, and there's our exclamation mark for factorial. So to put this in, you would type 10, math, over to probability, down to factorial, and there we have it. 3, 6, 2, 8, 8, 0, 0. So a combination is the number of ways to arrange something if order doesn't matter. Right? Like if I wanted to say, what about if I have a set like 1, 2, 3, 4, and I want to take 2 things from that? Well, yeah, then I could take 1 and 2, or I could take 2 and 3. But the main idea here is that there's no difference in a combination of making a group of person 1 and person 2, or making a group of person 2 and person 1. And there's a formula for getting the number of combinations. And that formula pertains to the factorials, right? If we have n things and we choose k of them, then to be in our group, right? Then this has number one, it's written like this. Its formula is decided by this. And I can show you how to get that once we talk about a permutation, because it's easier to see the formula for a permutation and realize that we're just kind of downsizing permutations to get combinations. But the main thing that I want to show you is that you can get that on the calculator. So let's see what they ask us to do here. They say a teacher wants us to divide a class of 15 students into groups of 5 for a class project. How many possible groups of 5 students exist? So this is 15, choose 5, right? We could take 15 factorial and divide that by 10 factorial, 5 factorial. That's fine. There's also a button, 15 NCR 5 on the calculator to give us the same number. So can you make a nice exercise of doing the canceling and multiplying you need to get that factorial formula to work? Absolutely. What about just doing 15 NCR 5? That will also work. There are 3,003 possible ways of arranging groups of 5, if order doesn't matter, out of a selection of 15 students. So this permutations, on the other hand, is the number of ways to arrange k things from n things if order does matter. And that we write NPR or NPK. I guess I'm mixing my K's and R's. My apologies. I've lost the ability to do. I'm just lagging really badly. NPK, and the idea is that let's see if we can figure out what that formula would be. How many different ways are there to pick the first one? Well, n ways to pick the first one, and then n minus 1 ways to pick the second one, all the way down to n minus k plus 1 ways to choose the kth one. And how could I get that from a factorial? Well, I could write n factorial, right, which would be all the way down, and then I could divide that by k factorial. And that's part of the combination formula. The other part of the combination formula is just how do I arrange sorry, I got that a little backwards. Right, this would be, we want k things up top. So that's actually n minus k factorial that we would need to cancel off from the bottom. And then how many different ways are there to arrange those k things? Well, there's k factorial ways, and all of those are the same combination. So we divide by that to mod it out for combinations. There's also a button on the calculator. So notice this one says the club has 20 members. They want to select 3 officers for next year: president, secretary, and treasurer. So then the order of selection matters. We're doing president and then secretary and treasurer. So they draw 3 names at randomly, and then they assign those. The first person is the president, the second person is the secretary, the treasurer, and the treasurer, right? So order matters in this case. When order matters, you want NPR. So we are doing basically 20 NPR 3. And so on the calculator, we could bust that out and say, what is 20? Math, over to prob, down to NPR 3. And that would give us this number, 6,840. So it looks like I'm reaching the 2.5-hour marker. And I have also now reached the end of my chapter 3 portion of the worksheet. And that seems to be a pretty good place then to stop for now. So let's leave it here, and I will come back in at a later time or in a class lecture, and I will finish up this last 3 pages of the worksheet and call that love. So I hope this was helpful. I will post these written notes up for your information, and we will continue as best we can. Thanks, and good luck with your studies.